Hello, eighth grade. Welcome to actually where I am right now. It's the guest room in my house. I'm glad you're watching this. I'll be sharing videos from here with you for the foreseeable future. But first of all, congrats to you. I hope things are going well. This is our first video, and most of the time it'll obviously be about science, but I also want to just connect, and I think having videos is a nice way to do that. My family and I, as I've shared with my advisees, we have been playing board games and doing puzzles, doing a lot of Xbox, won't lie. Played outside, lacrosse ball throws and basketball shots and the like. But this is a time too where we can connect. And I want to first off say, if you're watching this, good job. It means that you were, hopefully you finished up talking with your advisors, having a little face-to-face after actually hearing from Mrs. Pepino about what she's been doing in her welcome. And then you made it to the kind of landing page for what to do for science today. If you're watching this, hopefully it's March 31st, Tuesday. So you've made it here, and what you saw there was to go to this haiku page and to click, well, it's not there now because I'm making the video as we speak, to click this new and improved review video. My little intro now is a way of just sort of connecting with that, but I'm glad you've made it and you've watched it. The plan is, for this first day, is that I'm going to go over all of our notes, all of the Newton's Laws notes, just as a refresher, and then after you're done watching that refresher, I want you to click this homework. It was the one that was due before we left for break, and look that over, see how you did on that. And then the last thing to do is that it's not here yet because I haven't put it on assigned yet. There'll be your very last homework assignment. It's called Chapter 6, Lesson 3, Part 2. It's only like 3 questions. It's on Newton's third law. That will be it for the first day. So to watch this video that you're watching now, to look over your graded homework, this one here, and then to do the next homework assignment. That's your assignment for today. And then quickly, just looking ahead, we'll be doing Newton's Laws for the next couple classes, really for the next 3 classes, whatever you want to think of as classes, right, into next week. And then we'll be starting something in foreseeable future after that. For now, let's just worry about today. So here we go. Here is the review notes for Newton's Laws. You might have watched some of these videos in earlier units, and I had made those videos a couple years earlier, but I figured with all that's going on, I'm going to make a nice new fresh video for that. So I'm just going to go through these, follow along. If you have your notes in front of you, that would be good too, just to kind of look to see what's on here, and is what was written on the notes here, is that what you have down on your notes? That would be a good way to connect. So the first one, law of inertia. Newton's first law of inertia is all about how things are resisting a change of motion. Things don't want to change motion. If they're still, they want to stay still. If they're moving, they want to stay moving. And they will only change if they feel a net force. In other words, things don't want to change their motion, and how much they don't want to change their motion depends on mass. Things that are more massive have more inertia. More inertia means they don't want to change what they're doing or not doing. If they're at rest, they really want to stay at rest. And if they're in motion, they really want to stay in motion. Now, before we think getting into inertia a little bit more, a couple of reminders. We went back to remember about force. Force we had explored before when we did mechanical energy. Force is measured in newtons, Sir Isaac Newton. Force is a vector, meaning it has an amount, 5 newtons, 7 newtons, 100 newtons, and a directions, 50 newtons this way versus 50 newtons that way, up, down, left, right, north, south, some sort of directional component. And the big idea about force, in terms of Newton's first law, and really the second law too, is that acceleration, how much something changes motion, how much does something speed up or slow down or change its direction, that is acceleration. So how much acceleration happens depends on the amount of net force, the total amount of forces acting on something. More net force can create more acceleration. We also, oopsie, that's my distracting phone. Oh look, and it's Mr. Curry. All right, I'll text him back later. Jeez, I should put my phone away. Anyways, one specific force, again, this is a little bit of review, was the gravity force, the weight force, how much gravity is pulling down on something. And it's directly related to mass. How much force of gravity is pulling down on something is its mass times the acceleration due to gravity, which is always 10. So if something has a mass of 2 kilograms, 2 times 10 would be 20 newtons. So a gravity force, a weight force of 20 newtons, means it has a mass of 2. Anything, you take any mass of anything and multiply it by 10, that's the gravity pulling down force that gravity is creating, pulling down on it. Now, a new sort of force that's always kind of working against gravity force, so to speak, is what we call the normal force. Now, this is a new one we had not talked about in the last unit. So normal force is the resisting, pushing back up force. It's kind of against the gravity force. If there's a box sitting on a table, it's not moving, the forces are balanced. It means that, well, if it's 2 kilograms, gravity's acting on it and it's pulling down with 20 newtons of force, but the table's pushing back up. This normal force is pushing back up with 20 newtons. That keeps it from not accelerating. It's just staying where it is because the forces are balanced. That normal force we'll think about a little bit more as we go through. At this point, we did a couple net force practice problems. When you added the arrows or subtracted the arrows, remember doing those? Those problems were also reviewed from mechanical energy, but that's what we did then. Then we got into a little friction, another kind of force, the friction force. It's this force that resists the motion of things when they're sliding past each other. There's static friction that resists the start of motion. So if I have like my SCH, filled with tea now, a tea cup here, if I start to push it, you probably can't see it here, but if I start to push it, there's some initial resisting static friction. And if I push hard enough, I'll overcome that static friction and it'll start to slide. And that is then sliding friction. So one is resisting the start of motion, the static friction. And then once it does start to move, it's sliding along, then we have our sliding friction. Friction depends on two things. First is that roughness factor. How gritty and rough are the two materials that are sliding past each other? Sandpaper is more rough than smooth paper. So sandpaper would create more roughness, more friction if something's rubbing against it. And then there's the squeeze factor, as we called it. How much are two things squishing down together? Many times the squeeze factor has to do with gravity, because gravity's pushing down and normal force is pushing up, and things that are more massive are being squeezed between it and the earth, so to speak, because they're more massive, there's more gravity force. So if there's a big massive box, 20 kilogram box, thus having a weight force of 200 newtons, the squeeze factor is greater than if there was a less massive box that's being pulled on by gravity with less force, therefore the normal force is less. There's less squeeze factor. It's not pushing down on the earth as much as this one, therefore you could probably push it along easier because the friction would be less. Not always about gravity though. We use the guy stuck in the chimney, thinking that he could also increase friction between him and the walls of the chimney if he pushes really, really, really hard on those walls. If he increases his squeeze factor there, he increases friction so that it doesn't fall down. As soon as he lets go, he's decreasing the squeeze factor, friction force goes down, and thus he slides down due to gravity. Back to the first law, again some examples of it. Object at rest stays at rest. There's a bottle on the table. Unless an unbalanced net force acts on it, you could push the bottle and it starts to move. Or there could be something in motion. So if there's a ball that's moving along, it will move on forever until it, wham, hits the wall. That wall creates a net force that slows down the motion of the ball. It slows down its speed, which is another type of acceleration. It's accelerating in a negative way. All right, second law of motion, we've already kind of talked about this already. Truth be told, all three Newton's laws are all interconnected. They're all dependent on each other. So sometimes it might sound like I'm talking about the first, the second, and the third together. That's because they're all so closely related. So Newton's second law is all about acceleration. How much does something speed up or slow down or change direction? And that depends on the net force acting on it and the mass of the object experiencing the acceleration. Some object that's feeling more force, more net force, will accelerate more than something feeling less net force. Or something with more mass will experience less acceleration compared to something with less mass if both are feeling the same force. And here's the equation for that. Newton's second law is essentially this. Acceleration equals force divided by mass. A equals F over m, or written another way, a way we've seen it before, force equals mass times acceleration. So we thought about that in all sorts of different capacities of whether you want to accelerate something the same. If something's more massive, you'll have to push more force to make it accelerate the same. This had to do with the acceleration due to gravity, 10 meters per second. The force of gravity pulls on an elephant with more force, and because it has more mass, it accelerates the same as an object with less mass, though it's pushed on by gravity, or pulled on, I should say, by gravity with less force. So the acceleration of these two objects are the same when the force of gravity is the net force acting on it. And this idea too, if you wanted to move a basketball or a car, if you want them to accelerate the same, you'd have to certainly apply way more force to the basketball. If the same amount of force is applied to both things, well, the basketball will accelerate more because it's less massive. And finally, all that kind of pictures and images, we broke it down into this idea of saying if objects have if you change one of the three variables, how would the other two variables respond? This is essentially a comparison of all three of those things. In this example, if you have two objects with different masses and you want them to accelerate the same, you have to apply the more force to the more massive object. Or in this case, if you have two objects with the same mass, but you want this one to accelerate more, well, you need to apply more force to make this object with the same mass as the other one accelerate more. So again, look this over and think of ways of, we're basically describing acceleration equals force over mass by all of these diagrams, using this sort of, these pictures, this key, as a way of thinking about how one of those factors can affect the other two. Then we got into the friction lab. This is kind of where we ended class. We were working on this friction lab. We were wrapping up this friction lab back in mid-March when we last saw each other. This idea is that if you're pulling something along the ground, and if it's not accelerating, it's just going at a constant speed, no acceleration, all forces on it must be equal. Well, we know that there's a force of gravity pulling down on it. There's the normal force pushing up on it. And if it's not accelerating, it means that the force that you're pulling on it, the force that you were measuring, is the same as the friction force holding it, trying to hold it back. And if you measure the pull force, which you can see on your little scale, and it was just moving along at a constant speed, that means the friction force was that amount. So we looked at that as well. You also did some net force practice problems. And finally, we've gotten to Newton's third law of motion. These were the last little set of notes. That's right, we did these notes. We were about to do big paper review. Third law of motion is this: for every action force, there is an equal and opposite reaction force. Newton's third law is about equal and opposite action and reaction forces. So for every action force, there's an equal, in other words, the same amount of newtons, and opposite direction, because forces have to have both components. So basically, if one object creates a force on a second object, that second object creates an equal and opposite force back on the first object. Equal in amount of newtons, but opposite in direction. Always two objects involved, and this idea of if you push on something, that something will push back on you. I can push on the wall's pushing back on me. I can feel it. We take that a little bit further. A classic, I think a really helpful example, is to think about the person in the pool. If she wants to accelerate in this direction, she has to feel a force pushing on her to make that happen. She can make a force push on her if she pushes on the wall. She can make the wall push on her if she pushes on the wall. And the harder she pushes on the wall, the harder the wall will push back on her, the more she can use that reactive force to move through the water. We use that example of floating tennis balls in space. If you're floating in space, and I'm drifting away from the space station, I could use tennis balls and throw them in the opposite direction. I would push against the tennis ball would push against me, and as I keep pushing away tennis balls that I had for some reason, I can slowly push myself back to the space station. This is how rockets work, and this is how Wall-E used a fire extinguisher to move all around the spaceship in that movie Wall-E, if you'd seen that. Here's a couple examples. We talked about that: jumping or swimming that we just talked about, or walking. You move around because you push on the ground pushes back on you. That's how you move anywhere. The last slide was just this idea. Two objects, again, using kind of the same arrows and circles that we had used before. If an object creates a force onto a second object, that second object creates an equal and opposite force back on the first. What happens to those objects, though, is different. Even though they're both feeling equal but opposite forces, they'll travel away each other in an opposite direction, but the accelerations will certainly be different because this force is acting on a less massive object. It will accelerate more. This force, which is equal in amount, though opposite in direction, is acting upon a much bigger object, so it won't accelerate away as much. That's why the outcomes of Newton's second law, equal and opposite, are not always looking the same. An object might go flying away faster than a much more massive object that isn't. So that is the last part that we need to kind of keep in mind for that. So that's the end of the review notes. At this point, please do your last homework assignment. It shouldn't take too long. Drop it off in haiku like you normally would, and I will see you in 2 days' time on Thursday. Bye-bye.